Okay, so we did a bottom-up approach. We have seen that you can use symmetric crypto to encrypt files. You can use asymmetric crypto, for example, public key encryption, to transmit symmetric keys once you have a public key. But one very fundamental thing we haven't talked about yet is randomness. So, as we've seen, we need random keys for symmetric encryption, but also for asymmetric encryption. We need nonces that can never repeat, so they need to be as random as possible. We can do key exchange mechanisms. Unfortunately, we didn't have the time to go into depth on them, but they also need randomness. Well, essentially everything in cryptography, all systems rely on good randomness. So if you have an AES encryption of something, the encryption is really only as good as the key. Because if an attacker can predict the key, then the encryption was pretty much useless. So when we talk about randomness, we also have to introduce the topic of entropy. The term information entropy is what we call entropy in computer science and in cryptography. If you just Google entropy, you're going to end up at a chemistry website, most likely, because entropy stems from chemistry. And information entropy is the expected value of information content of a random variable. That sounds a bit odd, and as you probably know, as soon as there are signs like sums or integrals, something like that, usually people phase out. Information entropy is an interesting topic by itself. It's an interesting concept. It's about how much information is in a given message, essentially, and the more random the message is, the more entropy it has. But it's kind of abstract, so I want to introduce the term how we're gonna use it. Well, in the applied world, in the engineering world, when we say entropy, we usually mean by how many unknown bits did we receive. And with unknown bits, we mean bits that an attacker that observes our computer from the outside cannot predict. So, in order to get a little bit of an understanding, I want to give a couple of examples. You can maybe, on the individual example, pause the video for a second and think about it. So, 2 coins get tossed. What is the entropy of this experiment? Well, 2 times we get either heads or tails, so get an entropy of 2 bits. If we throw coins in order to generate key material, with 2 coins we would get 2 bits. Now a random number generator generates 32 bits, and the highest bit is always 1. How much entropy is that? Well, since 1 bit is fixed, this bit is predictable, because by default it's always set, so it doesn't add anything to entropy, so we have 31 bits of entropy. Next example, a random number generator gives us 32-bit integers, but only even integers. How much entropy is that? In this informal definition, I'm gonna write them. Well, it's also 31 bits. Because even numbers, the bit representation of even numbers always ends with a 0, right? Because the 1 bit is not set, so... Oops. Last bit 0 means even, so we have again 31 bits. Next example, we have an AES key consisting of 10 0 bytes and 6 truly random bytes. What is the entropy? That's kind of a trick question, because it's one of the first rules of randomness. In hindsight, you can never tell what is random and what is not. You see, the bit string, this bit string here, if we have a random number generator, this bit string is just as equally likely as all other bit strings of the same length. So an AES key with a lot of 0 bytes, in hindsight, we can't tell if it was random or not. We as engineers can just look at it and say, okay, it looks fishy. But as I said, in hindsight, you never know if something is actually random or not. Last example. A random number generator gives us 64-bit integers, but only 1 out of 8. So say it has an internal state of 8 integers. Each one of them is 64 bits long. So what entropy does that give us? Well, since there are only 8 integers, we have an entropy of 3, right? Because in the end, how long the integers are doesn't matter. The relevant part is that the random number generator only outputs 1 out of 8 possibilities. See, 2 to the power of 3 is 8, so we have 3 bits of entropy.